actually Donald Fagen walk through the raindrops, because we're going to be talking about walking through rain again, like we've been doing for the last 4 or 5 times. And then one of my favorite groups, 3-Track Mind. They never made it. They were just a local group in the Seattle area, but they're still to this day one of my favorite groups, and I love that song in particular, Sacred Fire. Okay, so that's what we're doing today. As always, anybody want to come up on the stage and hang out and be ready to interrupt me when I say something stupid, just raise your hand. We'll bring you up. I've got my best buds here, 2 versions of Shamash in the form of Shamash and Logic Guy. How you doing, Shamash?
Hello. Good to be here.
Good to see you. And Andy, hero protagonist. You're riding your bike today, Andy, or are you...
No, I'm just standing in my yard.
Just standing in your yard. You got to move, man. Use it or lose it.
You're right. I might start a bike ride sometime during this talk, so we'll see.
Okay, well, just don't turn off your brain. Let's see. So what do we say about this? First of all, of course, as always, the Scientific Discourse House is about bringing well-established science, talking about it a little more rigorously than you usually hear science talked about, primarily because it's well-established science, not the kind that often attracts more attention, the kind of wow, gee whiz, maybe this is true, speculative, and usually pretty mathematically complex things at the cutting edge of physics. We don't do that in general, although we may allude to those things from time to time. So we're finishing up an exploration of 18th and 19th century ideas, how our ideas about light were formed by looking at the heavens and looking at features in particular centered around, but certainly not exclusively, the phenomenon called stellar aberration, the fact that the light from stars that reaches us gets twisted into a slightly different direction, either, depending on how you want to look at it, either because of our motion relative to the rain of particles coming down, or just because when we move, the light, the object relative to us was in a different place when it emitted that light. Kind of 2 different ways of looking at things. And a lot of the features of our understanding of light today came from wrestling with how to understand aberration in the corpuscular view of light, which reigned in the 18th century, and then the wave theory of light, which reigned in the 19th century. They both had kind of nice features, but they brought with them some baggage, which was difficult to deal with. In the case of corpuscular theory, why light even had a speed. If light was made of particles, why would those particles have to move at any speed? Why couldn't they move at any speed they wanted to? That was kind of a weird thing. The wave theory solved that problem at the expense of making us accept the idea of a privileged reference frame to look at light in, that there was one reference frame, the frame of the medium that the waves travel through, that was more important, that was the important frame, and that if you were moving relative to that frame, you'd see light doing different things, but that would be a result of your motion. And not unlike the case with corpuscular theory, which allowed any observer to think of themselves at rest. In classical Galilean relativity, that was the nice thing about it, was the ability for anybody to think of themselves being at rest. Go ahead, Andy. Oh, you unmuted. Maybe that was accidental.
That was unintentional, sorry.
Okay, all right. Okay, so let's go ahead and get started. I've titled today's The Final Failure, because there's been several failures along the way. They've been interesting failures. I always put them in quotes because of the kind of different way to understand it. Is it a failure or is that a win? In science, whenever we fail, that is a win because it tells us something that we thought we knew wasn't true. So this is the final failure that we're going to talk about and its resolution. There's links there, as always, to all of the old bites of physics, nibbles of physics, and just all of my public documents in general, a lot of which are flat Earth related, I must confess. This whole series really comes in part from things that I looked into as a result of talking with people who believe that the Earth is flat. And it's a never-ending source of astonishment to me that I have learned so much from those conversations. But I have to confess that it's true. Let's see. What else was I going to say about all of that? I guess nothing else. Let's just go on then to the first slide. This is a review of part 4. So part 4 was largely devoted to the 19th century. And we started off with Arago, who was looking for corpuscular speed differences that would manifest themselves in the refraction of light from stars. He pointed a telescope at different stars, let that light pass through a prism on the way out of the eyepiece, and expected to see different amounts of refraction depending on the different speeds of the light coming from the different stars. And he didn't see anything. Around that time, the wave theory was picking up support. But that wasn't much help to Arago, because it would seem to make the same kind of prediction. Now, not because of the light traveling at different speeds so much. The wave theory would give a speed to light. It would be the speed of the light in the medium that it's traveling through. But because we would be moving relative to that, or the star would be moving relative to that, there ought to be different kinds of refraction as well, in particular because of our motion through the ether, as it was called. So in 1818, Fresnel hypothesized a thing called partial ether drag, and it was motivated precisely and exactly by trying to explain why Arago hadn't seen anything. Trying to support. Fresnel was a wave guy. He was totally committed to the wave theory. And he said, well, okay, what if this? What if materials drag the ether with a velocity that is a fraction of that material's velocity with respect to the ether? So if you have some material moving at 10 miles per hour, maybe it drags the ether at 5 miles per hour. Some fraction, that fraction would be determined by the so-called index of refraction of the material. N, which is the ratio of the speed of light in a vacuum to the speed of light in the material. It was known that light would travel at lower speeds within transparent media. And why did he say that? Well, he said that because he knew that if it did that, Arago wouldn't see an effect. And Arago didn't see an effect. So he was doing really nothing but trying to come up with some hypothesis that would account for it. It was not based on any theoretical considerations other than trying to explain Arago's result. And that's okay, right? That happens in science as well. It's unsatisfying because it looks like what's called a special pleading. It looks like you're just trying to say, okay, well, here's why that happened. And then, but does it work anywhere else? That's the question. In 1820, Poisson, who was a committed corpuscularist, tried to kill the wave theory by pointing out that Fresnel's theory, which was highly mathematical, involved interference of waves coming from different sources, that every source makes waves that then become themselves sources for new waves, and it's the interference of those waves that create the effects at more distant points. And he pointed out that Fresnel's wave theory made this seemingly absurd prediction, the so-called Poisson-Arago spot, a spot of light in the center of the shadow cast by a disk. An opaque disk would cast a dark shadow, except Fresnel's theory would suggest that there should be a bright white spot right at the middle of that, a tiny little bright white spot right at the middle. And he thought he had done it. He thought he had shown that the wave theory was nonsense. And then Arago himself quickly did an experiment and showed that the spot predicted by Fresnel's theory did exist. And that was one of those kinds of things where if you imagine the reaction to that, Poisson had suggested that Fresnel's theory makes this ridiculous prediction, and then Arago shows that that ridiculous prediction is borne out in nature. That was a supreme triumph for the wave theory, and it went on in subsequent years to do better and better. So the wave theory was ascendant shortly after 1820. In 1845, Stokes proposed a different kind of an ether drag mechanism based on an actual theoretical analysis that also dragged some of the ether outside of a medium with it. I confess I don't completely understand Stokes' theory, but it made a different prediction than Fresnel's theory did, or Fresnel's hypothesis did, in a case that Fizeau, then in 1851, tried out. Fizeau conducted an experiment to distinguish between Fresnel's empirical hypothesis and Stokes' full-blown theory. And Stokes' full-blown theory didn't work. Fresnel won. The Fresnel's simple hypothesis was actually now for the first time verified. Up to that point, his hypothesis was just used to say, well, if this is true, then we won't see anything. If this is true, we won't see anything. And then Fizeau's experiment was actually to measure ether drag itself. And the amount of ether drag that he measured was the amount that Fresnel predicted. So that was another major success for Fresnel. And at that point, Fresnel looked like he was on to something. And then we mentioned last time that this guy Klinkerfues in 1867 tried to look for enhanced aberration, stellar aberration, in a water-filled telescope. And he claimed to find it despite the fact that Fresnel's hypothesis would rule it out. Fresnel's hypothesis, if true, would mean that Klinkerfues should not have seen any enhanced aberration in his water-filled telescope. So that looked like trouble brewing, but it was particularly puzzling because at this point Fresnel's hypothesis had successfully explained other failures to observe the ether and had been empirically verified, specifically the 1 minus 1 over n squared fraction that I mentioned above had been specifically verified by Fizeau. So that was pretty weird. And a few years later, Airy looked at that and said, somebody needs to replicate this. He doesn't say it, but I think it's pretty clear that Airy must have expected that when he tried to replicate it, he would fail because Fresnel's hypothesis suggested that it shouldn't be there. And indeed, when Airy tried to replicate the result, he failed. And this is a relatively famous thing that is called Airy's failure, even though I think most people believe that Airy must have almost undoubtedly expected to fail and really just verified once again Fresnel's hypothesis. So that brings us up to kind of where we start today, and I'll just stop there for a second, see if there's any comments or questions. And I'll welcome Ben Tristram to the stage. Hey, Ben, good to see you. It's been a while. We haven't talked much.
Yeah, how are you doing? Yeah, looking forward to listening in this spare moment.
Good. Before family time. Ben's over there in merry old England, and it's always getting to be about dinner, family time about now. That bad on me for doing this at the wrong time. Okay, so let's move on then to slide 3. So in the 1870s, after Airy's failure, if you want to call it that, it was a pretty happy time in physics. There were a lot of people who really thought, okay, we've got this. We pretty much have everything down. We got Newton. We now have Maxwell. We haven't talked about Maxwell and his work in electricity and magnetism, but Maxwell came along in there. We didn't talk about him last time, but in the midst of all of this, he very solidly established that not only is light a wave, but that it's an electromagnetic wave. It's a wave of electric and magnetic fields. So that's a kind of a cool thing too. We'd had Bradley's observation of stellar aberration, and as well as stellar parallax, which is another thing we didn't talk about, but that was observed finally. Bradley was looking for it. He didn't see it because it was much smaller than he didn't have any reason to expect it was anything. But it turned out the stars were much further away than Bradley's apparatus could have detected. But things got better, technology advanced, and a century later, stellar parallax was observed. Both of these things are ample confirmations of the heliocentric model and Newton's simple accounting for the heliocentric model. I don't emphasize that enough, how simple Newton's laws are. Masses attract each other, inverse r squared, product of the masses, and forces cause acceleration. That's it. Right? You put those two things together, you explain everything that we see in the heavens, at least at the time. That was a massive success, but it did suggest very strongly that we had to agree with Copernicus finally and know that the Earth was not at the center of the universe, that it orbits the sun. And that orbit was amply confirmed by both the observation of stellar parallax and aberration, both of which require the Earth to move around the sun to produce those effects. And as I said, the wave theory of light was solidly established via interference effects and fully accounted for via Maxwell's work, which also, on the side, unified electricity and magnetism. And despite the troubling lack of theoretical justification, Fresnel's partial ether drag hypothesis both accounted for multiple failures to observe the motion of Earth, and it had been directly experimentally confirmed in value, the 1 minus 1 over n squared thing, which is weird, right? And there's no theoretical justification for that, but that had been directly experimentally confirmed in Fizeau's experiment, experiment. And I put a link there to a really great source that I just found in preparing this thing. So if you are interested in exploring any of the rabbit holes that I continue to explore, and there are myriad rabbit holes, this is another really great source. You might want to just copy that link and put it somewhere else for future reference. So let me stop there again just for a second, see if anybody has any questions. Maybe see if there's anything in the chat. Okay. Oh, let's see, we got Astro Boy. Let's bring up Astro Boy. See if he's still down there. Oh, I think maybe we lost Astro Boy. Sorry, I didn't PTR myself. Must have missed. Oh, there he is again. Let's try. Hey, Astro Boy, welcome to the stage. Got anything, or you just want to hang out with the cool kids? Oh, okay. Well, maybe we'll see him later. All right. So let's move on to slide 4. A quick review. This is really important for later, for kind of the punchline of this whole episode. And that is to recall that Fresnel's hypothesis was that the ether is dragged by a medium in a way that depended on, 1, the velocity of the medium with respect to the ether, v, and 2, the index of refraction of the medium. And as I say, this is just a purely empirical law meant to explain the failure of Arago and others to detect the motion of the ether. And as a result, in the Fizeau experiment, where he's got light going in opposite directions through water, one with the water, one opposite the water, Fresnel confirmed that the velocity of the light in the water, as measured in the lab, was c over n, that's the velocity of light in the water, plus the velocity of the water times that fraction, that weird 1 minus 1 over n squared thing. He just experimentally got a value which was within his precision of that value. And so he had confirmed the Fresnel hypothesis. We've got Astro Boy again here. Are you? I'll give you one more shot here. Did you have something to say now, or do you just want to hang out for the moment? I'll take that as a just want to hang out for the moment. We'll have more chances here as we go on. Okay, so feel free to stop me as we move on here to slide 5 if there are any questions on that. But just remember, we're going to refer back to this slide 4. It is a preview of the punchline of this final episode in the series. So I want to take a moment here to talk about a thing that will come up a few times in the rest here also, and this is the idea of first order, second order thing in physics and math. And I want to do it in particular by looking at this Fresnel ether drag thing. Because ordinary objects move at speeds that are far less than c, Fresnel's hypothesis predicts only a small addition or subtraction to the speed of light. The speed of light in the water is c over n, right? And that's the first term in that in the velocity that Fizeau saw. He saw c over n, but then he saw plus this partial ether drag thing. And that partial ether drag thing is very small compared to the speed of light in the medium. It's v times 1 minus 1 over n squared. If you compare that v times 1 minus 1 over n squared to the speed of light in the medium, which was c over n, in other words, just take the ratio of those two things, you can write that as v over c times n minus 1 over n. That's just a little algebra to get to that. But I write it that way to show that ratio, that the ratio of the addition that Fresnel's hypothesis gives to the speed of light to just the basic speed of light, c over n, is a really small number, v over c, times a number that's basically 1. And the index of refraction of water is 1.5. So that the final thing there is 1.5 minus 1 over 1.5. And frankly, that's really close to 1. And I wouldn't care if it was 5. I would still say it's just a number on the order of 1. And so when we talk in science about things being on the order of, we mean something like within a factor of 10 of. Sometimes we mean within a factor of 1,000,000 of. But in this case, we'll say something like on the order of really mean within a factor of 10. So that ratio then of the thing that we add to the speed of light with the Fresnel hypothesis is on the order of v over c, which is a very small number. That's a really small number. It's on the order of that because the final term, the n minus 1 over n, is just a number that's on the order of 1. It doesn't change the fact that the basic quantity there is on the order of v over c. And we're going to use that language several other times. And part of the reason for introducing it here is to ask the question, what if the ether motion with respect to the ether produces other effects that are on the order of v over c squared? What if there are additional effects beyond the partial ether drag that are of second order in v over c? That wouldn't be a problem for anything we've seen because none of the experiments that were done at that time were sensitive enough to see anything like that. If there were effects on the order of v over c squared, they'd be much, much less than the effects on the order of v over c, just because v over c is itself a really small number and v over c squared is a really, really small number. So that was kind of, where we were also in the 1870s. People didn't necessarily expect that to be a problem, but they understood that we hadn't really ruled that out yet. Okay, I'll stop there again.
John, Yeah. Before you move on, very quickly, on the previous slide, on slide 4, we had this formula that we saw last time. So C over N plus V into 1 minus 1 over N squared, and then in the next slide you divide the two.
Right.
What is the division expressing here?
Okay, good. So in other words, what I'm trying to do is I'm trying to show that second on slide 4, that amount that I'm adding. Notice the speed of light in the water is c over n, and so the question is, well, why didn't Fizeau just see that it's moving at c over n? And Fresnel, well, you might say this. You might expect this. Maybe the light should have moved at c over n plus v. That would be the expectation if you think that the light is moving at speed c over n in the water, and then with the water moving at speed v relative to the lab, you just add that v. But Fresnel said, no, it's v times 1 minus 1 over n squared, for no reason other than the fact that that's what it needed to be to explain the Arago's failure. And so all I'm really doing in slide 5 is introducing the idea of order of, in the guise of just comparing that little term that I'm adding, because this is what Fizeau did. Fizeau wanted to measure that term. He didn't care about the c over n. We already knew that. He wanted to measure the really small term, the v times 1 minus 1 over n squared term. And that's what he did pretty accurately. But the point here is just to show that the thing he measured is really small. And one way to see how small it is to compare that thing to the c over n itself. So divide the v times 1 minus 1 over n squared by the c over n to see just how much smaller it is than c over n. And you can see that what you get is that it is smaller essentially by the ratio of v to c. It's v over c times a number on the order of 1. I see how this doesn't make a lot of sense yet. I think it'll make more sense as we move into the Michelson-Morley thing, which is what we're going to do now. But all I'm doing there is just comparing the two terms and showing that the second term is smaller by the ratio of v over c. If there were other terms in the, in that drag equation that were maybe proportional to v squared, then they would be down by another factor of v over c squared. And it's not maybe obvious why the c comes in there. But anyway, I think it'll become more clear on slide 6. So let's, unless you have a follow-up. Yeah. So the question is, what if the ether does produce effects on the order of v over c squared? We haven't ruled that out because Fizeau simply wasn't sensitive enough to see things on that order. That's really, really small. So this is where Michelson and Morley come in with their interferometer, and I'll just really point to Bita Physics number 52, which was specifically on the Michelson-Morley interferometer and the experiment, the Michelson-Morley experiment. So you can get more information there. I'm just going to steal a couple of things from that. So if we go to slide 6, as you will remember if you were here for Bita Physics number 52, in the Michelson interferometer, first of all, let's look on slide 5, where I've got a picture of it there, just to remind ourselves of what it does. You have a source of light, which travels to a beam splitter in the center, and that beam splitter allows some of the light to travel through. It's a partially reflective mirror. Some of that light travels through and then bounces off a fixed mirror and comes back. And some of that light gets deflected over there to the so-called movable mirror, and it comes back. And then the light from both of those different paths hits the beam splitter again, Some of it's reflected or transmitted in a direction I don't care about, but some of it ends up coming to the detector. Some of the light from the fixed mirror reflects off the beam splitter and comes to the detector. Some of the light from the movable mirror passes through the beam splitter and comes to the detector. And on the detector, you see this fringe pattern. And we talked about why you get those circular fringes in Bitophysics number 52. I won't review that here. The net result is that if you, for instance, if you did anything you get that interference pattern because of the fact that light coming to different places on the detector itself have traveled slightly different distances. Sometimes they travel by a difference in distance that is a half a wavelength, or 3/2 of a wavelength, or 5/2 of a wavelength. And if so, then when they come to the mirror, they are exactly out of phase and they cancel, producing a dark fringe. Whereas if they've traveled an extra if they've traveled an extra 1 wavelength or 2 wavelengths or 3 wavelengths, then they will actually get to the detector in phase, constructively interfere, produce a bright fringe. So you see a pattern like that. And if you, for instance, do anything to change the path length by just bumping one of those mirrors so that it kind of moves a little bit, that fringe pattern will change. Let me ask, I've got some people trimming trees outside. Is that just horrible? Okay.
Just below horrible.
Below horrible. Okay, good. I'm sorry that I can't do anything about it. My wife told me that it turned out they were coming today. I would have had them come another time. Anyway, so we'll continue with below horrible. Actually, I think I can maybe do something if I turn my mic down and speak a little closer to it. I'll try to do that. All right, so that's how the Michelson-Morley apparatus works. And now if you imagine, still on page 5, looking at the apparatus, if you imagine that apparatus is on the Earth and the Earth is moving through the ether, then some of those paths may be affected by moving perpendicular to the ether, maybe, or maybe they move with and against the ether, or maybe they both move across. But you can rotate this apparatus, and if the Earth is moving through the ether, then when you rotate the apparatus and exchange the roles of the paths, one path that was perpendicular to the motion now becomes parallel, the other path now becomes perpendicular. The very rotation of the apparatus should reveal the motion of the apparatus through the ether in a fringe shift. You should see the pattern shift. Now, that's only, of course, if the Earth is moving through the ether. So maybe it isn't. Maybe the Earth is not moving relative to the ether. But if it isn't, then it surely will be 6 months from now, because 6 months from now it's moving 60 kilometers per second the other way. And so then you would see it as well. Unless, of course, unless the Earth drags the ether with it. And we've already seen reasons to understand why that would conflict. That would conflict with observations of stellar aberration. And I don't want to go through that, but people thought about all this very carefully and became convinced that and Michelson-Morley certainly became convinced that they would see this. We'll talk about that in a second. So just to get at the numbers on slide 6, unless there are questions. On slide 6, then, I look at the actual, this is just a repeat from the Michelson and Morley Bitophysics. We calculated the times it takes if the ether wind is to the, first of all, if there's no ether wind, you get, no effect, of course. Assuming the path lengths are the same, you're going to have it take the same time to go along either path and back. But if there is an ether wind to the left, that means that effectively the apparatus is moving to the right through the ether wind. And now the up-down path becomes kind of a diagonal path, and the back-forth path becomes kind of a Fizeau-like, moving with the ether and then moving against the ether. Both of those motions produce differences in the times taken, but the differences they produce are themselves different. So if the ether is moving, then the time it takes to move along the up-down path, number one, is given by that 2L over C times 1 over the square root of 1 minus beta squared, where beta, remember, is just V over C. It's just the thing we've been talking about, the ratio of the speed of the ether, or the speed of U through the ether, to the speed of light. Whereas the time taken on path 2, the back and forth path, looks very similar. It's 2L over C times 1. The only difference is now it's 1 over 1 minus beta squared, not the square root of 1 minus beta squared. So they are different because the square root of 1 minus beta squared is going to be different from 1 minus beta squared. And on slide 7, I'll pretty much just say here, if anybody's interested in the details, I can show you the details. But it's pretty easy to show, it is easy to show, that time difference, which I've written out there, it's just 2L over C times 1 over 1 minus beta squared minus 1 minus the square root of 1 minus beta squared. With a couple of approximations, of good approximations, you can show that that's approximately just L over C times beta squared. So in other words, that time difference depends on, is a second order effect in V over C. It's the kind of thing that no experiment previously was sensitive enough to detect. In the case of Michelson and Morley, in order to be able to see that time difference, Oh, I see. I jumbled my English there. Anyway, what I wanted to say was for that time difference to produce one fringe shift in the interference pattern. I'm trying to change that while I talk here. For that time difference to produce one full fringe shift in the interference pattern, it would have to be, here's that word again, on the order of the period of a light wave. And you can go off and look up the speed of light and the wavelength of light and work out that the period of visible light is about 10 to the minus 15th seconds. It's really fast. It takes 1 femtosecond for light, visible light to oscillate one time. That's really small. So they had to be able to actually detect a time difference of 10 to the minus 15th second. So what else is there in that form? That's what the T2 minus T1 would have to be. Well, let's look at the other things. Because of Earth's motion around the sun, Michelson and Morley knew that they could expect to see beta, the ratio of the speed to the speed of light, on the order of 30 kilometers per second, the speed of Earth, divided by the speed of light, 300,000 kilometers per second. So they could expect to see betas on the order of 10 to the minus 4th. And the only thing under their control for the experiment was L. They wanted to make L as big as possible because they wanted to be able to detect really small time differences. The bigger L is, the smaller the time differences they would actually be able to detect. So they used a really big interferometer. Their interferometer that they did their final experiment with had arms that were 11 meters long. This is an enormous interferometer. So the ratio of that length to the speed of light, L over C term, is about not on the order of, but is about 4 times 10 to the minus 8th seconds. Takes about 4 times 10 to the minus 8 seconds, 40 nanoseconds for light to travel along one of those arms. So their expected time difference was on the order of, you look up above, L over C, which is 4 times 10 to the minus 8 seconds, times beta squared, that's 10 to the minus 4th squared. That gives 4 times 10 to the minus 16th seconds. That's about the same as the order of the period of a light wave. And this was more than sufficient for them because they were able to detect, they were able to accurately measure tiny shifts in the fringe pattern. The fringe pattern didn't have to shift through one full cycle. If they saw the fringe shift at all, they could measure how much it shifted and measure tiny fractions. So this was more than enough for them to measure the velocities that that they knew existed for the Earth.
How did they make sure that in rotating their apparatus, it didn't move the tiny amounts, change it dimensionally, the tiny amounts it would have to produce a similar effect?
Yeah, well, that's a good question, and I don't know the answer to it. I'm assuming that at some level they probably checked that by simply rotating it to 90 degrees and then rotating it back, rotating it 90 degrees, rotating it back, and just making sure that the result didn't was repeatable. I would think that would be a satisfactory way of checking that out. You think? I don't know. I really don't know. It's an important question. Of course,
Yeah, I'm not convinced because it's such a tiny expansion or contraction that you could imagine a lot of reasons why that might happen. But
just stress-wise, you mean? Yeah, mechanical
yeah,
stress or something. Yep,
and it could be a
that's true.
systematic reason why it does that when you twist it through 90 degrees,
Right.
depending on how the table's set up. I mean, I can't immediately imagine what it could be, but it could be thermal. It could be more heat coming from one side of the room, and it's just, I don't know. There could be reasons why you could flip it through 90 degrees and see a consistent change that isn't caused by that. I'm wondering how you control for that.
Yeah. Go
Wasn't
ahead, Andy.
one version of the experiment was floating in a vat of mercury,
That's true. That's right.
so it could be rotated just freely. And also, I think that was kind of a vibration isolation. I just thought that was cool. Where
Yeah,
do you get that
that's
much
right.
mercury?
Well, it doesn't take much mercury. An interesting kind of side to that, I once went to visit the Mount Wilson telescope, 100-inch reflecting telescope built, about the time of Einstein. And it is a really Gothic looking instrument. It just looks so 1800s, the way it's built. But the whole thing, this monstrous telescope, floats in mercury. The entire telescope floats in mercury.
So is that more for like vibration isolation, or is it as like a bearing, like to move it?
Right. I suspect it's probably as much as anything the bearing, just the ease of motion probably. But I don't know. It's a clever thing, obviously. And the point is that I don't know how much mercury they use, but you wouldn't have to use more than a liter of mercury to do that if you designed the vessel that it floats in, well enough, right? All you have to do is make sure that there's nothing but mercury touching the telescope and nothing but mercury touching the cup that the mercury's in, that the telescope is floating in. So same kind of thing with Michelson-Morley, I guess. But yeah, no, these are all things. This is where I'm glad I don't have to put my experimentalist's hat on. The things that you have to think about and care about and try to make sure you've put it. I'm sure that Michelson and Morley fully worked that stuff out. And the proof of that, of course, is the fact that I'm trying to take a historical approach here, but the Michelson-Morley experiment or analogs of it have now been done to fantastically greater precision than they did with the same result. So that's always worth keeping in mind, even though I think it is really important when you're doing a historical survey that you understand what they knew at the time they did it. So I don't like to lean on that too much. Okay, so let's see. So what were the expectations then? Here's where Michelson and Morley were. They knew that because the index of refraction of air is basically 1, that Fresnel drag coefficient is basically zero. There's not going to be any Fresnel drag. They're not going to have a problem with partial ether drag at all. They also knew that there had to be an ether. If light, they knew that light was a wave. Waves require media. There wasn't any question in anybody's mind in the late 1800s that there was an ether. There simply had to be, even though it hadn't been detected. And for those reasons, and finally, they knew that their apparatus was sensitive enough to detect the differing velocities of Earth over 6 months. That they knew existed from its motion around the sun. So they knew for sure that they were going to detect the motion of their apparatus through the ether. There was nothing that was going to prevent them. They had an apparatus that was sensitive enough to measure motions that they knew existed, and Fresnel wasn't gonna help, wasn't gonna cause a failure, both because they were looking at a second order effect and because of the way Fresnel depended on the motion of the medium, which in this case was basically a vacuum, the air itself. And I put the analogy here because I think it's a really important one. People were saying the same thing when they were building the Laser Interferometer Gravitational Wave Observatory. When they were building it, we knew that gravity waves existed. There was copious evidence that gravitational waves existed, even though they hadn't been directly detected. We had detected their effects in the decay of orbiting pulsar neutron star systems. A Nobel Prize had been awarded for that. And we knew that the observatory would be sensitive enough to detect gravity waves produced by sources that we knew existed. We knew that because of these possible sources, not possible sources, because of sources that we knew existed, and because of the gravity waves that they would produce, we knew how the amplitude of those gravity waves, and we knew that this detector was sensitive enough that it would detect them. So we knew for sure that LIGO was going to directly detect gravitational waves. Unless something that we thought we knew was wrong. And in the case of LIGO, we weren't wrong. So almost as soon as we turned it on, we detected gravity waves, and now they're seeing gravity waves, I think, basically every day, especially from sources that they didn't even really expect, merging black holes and merging neutron stars. So that's been kind of the big. So gravitational wave astronomy is now a thing because they do exist. LIGO observes them, and it's now just a daily occurrence, basically. But that wasn't the case with Michelson and Morley. So we move on to slide 9. In the case of Michelson and Morley, they failed to detect the thing that they knew they were going to detect. There was no apparent, there were no fringe shifts at all at the level that they could distinguish. So something was very wrong. And as I say, although it's not historically relevant, it's important to understand that the fact that they didn't see anything has now been confirmed. People have looked with much more sensitive equipment, orders of magnitude more sensitive equipment, and it is still a failure. There is no motion detectable through the ether. So something we knew was wrong. And now the question is, well, what is that? And so I point out here a couple things. We'll have a brief discussion. To this day, there are those who think that the thing we knew that was wrong is that the Earth moves. If the Earth doesn't move, then it's no surprise that Michelson and Morley didn't see any motion through the ether. Presumably, the Earth not moving means that it's stationary with respect to the ether. Now, you could check that out, I suppose, by moving the apparatus itself. These days, we have, as I understand it, there are versions of Michelson and Morley using Fabry-Perot interferometers that are sensitive to motions of millimeters per second. So you could put this thing on a little mercury, supported track and just push it along the track at a centimeter per second and detect that motion, I suppose. I don't know. I honestly don't know if people have done that or not. Another rabbit hole I need to go down. But that is one thing that flies in the face of all of the evidence that it does. You have to somehow then explain stellar aberration and parallax, and there are bizarre ways to do that, but they are truly bizarre. So that's one thing. I do want to just open it up here too a little bit if there are any other ideas. But the other part, the other thing that people think, there are people who think today that Einstein was motivated to produce the theory of relativity primarily because of the Michelson and Morley failure. And that's actually not the case either, as we'll see on the next page. But obviously what we ended up coming up with was the idea that apparently our thinking that there was an ether, either our idea that there was an ether or our idea that it ought to have noticeable effects of any kind, was wrong. And both of those things then kind of get into philosophy. I mean, maybe bring Shamash in here. What's the difference between having an ether that can't be detected and not having an ether? Shamash, any ideas on that? Any thoughts on that?
I don't know. It depends on how you want to construct your theory, because at this point this is an aesthetic preference. You can say, oh, I have a physical theory and its success is identical to the success of another physical theory, because whatever test you do in theory A, you get the result up to a certain accuracy. You can do it under theory B. However, theory B has more assumptions in it. So theory B presumes that this ether exists in a certain way and it has very small effects so that we don't notice it, but it still exists because light is a wave and waves do pass through a medium. That's a law.
Yeah.
Well,
I like
yeah. Empirically,
But,
you cannot tell them apart. That is the thing. But there is an aesthetic preference. No, we don't want that, because that just requires more assumptions that are not based on physical reality.
right.
Or at least
No, I
not,
like that.
let me be accurate here. They are based on physical reality because both theories are empirical in a way. But the terms in one of those theories are not directly observable. So the logical positivists will throw it in the trash can, for example.
Yeah. No, I like that. I like especially the bringing the aesthetics in, because it is ultimately that aesthetics thing. Most physicists, certainly including Einstein, are kind of repelled by the idea of a theory that depends on something that can't be verified. That's kind of flies in the whole face of science. If something can't be verified, can't be falsified, maybe I should go to Popperian. As you know, I'm a big Popperian myself. If it can't be falsified, then it strikes me certainly as something that we shouldn't be including in our theories.
Whether it is falsifiability or direct observation or operational definition or whichever one of those schools you want to take. When we did the room about scientific assumptions, I think the one we've talked about, I think I'm proud of myself for capturing it beautifully. It's about interaction. So it's something that you interact with at any level of interaction. If it's repeatable, then that thing exists. And so when you say there's an ether, but I cannot interact with it, it's just the blue fairies at this point. It has no, there's no experiment. So whether you want to think of it as, oh, there's no experiment, so we cannot verify it, or there's no experiment, so we cannot measure it, or there's no experiment, so we cannot define it using other physical terms, or there's no experiment, so because we cannot falsify it, whichever one of those philosophies, at the center, there's that idea of interaction. And if we cannot interact with it, then it should not be part of the physical theory.
And I see Wissam reacting to my love for falsification. Sorry, Wissam, you will never break me. I'm a big falsifier. Okay, and it's so wonderful to be able to just shout at Wissam. He never shouts back, right? He's always down there in the goo.
That's what you like, okay. Wissam, are you proud of me shouting back? Am I doing a good job? I don't think I am. I think you have much more energy.
Okay, well, let's move on then to slide 10. In slide 10, I just show the first page of Einstein's 1905 paper in which he introduced the special theory of relativity. And you notice right off the bat, what is it called? It's called On the Electrodynamics of Moving Bodies. What? Where did that come from? And if you read it, it's a really interesting paper to read. It has all of special relativity in it. And the first part, he talks about electricity and magnetism, Maxwell's equations right there in that first page. But then he spends a few pages talking about kinematics, the kinematics in a world in which there is no preferred reference frame, and yet Maxwell's equations hold, giving a speed of light. What is a world like that has a wave thing that travels at the same speed regardless of who's measuring it, and that has no preferred reference frames? What is the world like? And he simply works out the immediate consequences of that kinematically. But he does that basically in service of his lingering puzzlement over Maxwell's equations themselves, which have embedded in them this kind of different, that Maxwell's equations don't obey the so-called Galilean transformation, the thing that underlies all of Newtonian physics. There's a fundamental conflict, and that conflict is most easily seen in the fact that they predict a speed of light without ever having told you anything about a medium. You get, unlike in the case of sound waves, where you start with air at rest, and then you imagine disturbing it, and you ask how fast does that disturbance travel through the air at rest. Unlike waves on water, where you start out with water at rest, and then you disturb the surface of the water, and you ask how fast the water waves travel with respect to that. Unlike a string at rest, perturbed, unlike every other wave phenomenon we have, Maxwell's equations are just telling you about how electric and magnetic phenomenon work, and if you manipulate them in a certain way, all of a sudden you get this thing that everybody knew was a wave equation. And it predicts a speed for waves. But you have never put into them anything about a medium. There's nothing in the equations that suggest a medium. And Einstein was really puzzled by that, and he was trying to reconcile that. The Michelson and Morley experiment and the implications of that provided kind of a way of tying it all together if one simply took Michelson-Morley result at face value and accepted the fact that it didn't matter what your motion was, you would always see light traveling at the same speed in any direction, in a vacuum, right? Or in a medium that you are, as long as you are at rest with respect to whatever medium you're in, it doesn't matter what that medium is doing with respect to any other frame. So anyway, so that's the thing, and I wrote down there at the bottom the what are called the Lorentz transformations. I wanted to do that just to take a moment here and note that these are the kind of simplified Lorentz transformations, the transformations between position and time that you get if a reference frame is moving. If you imagine a typical Cartesian coordinate system with x, y, and z, mutually perpendicular axes, and then you imagine another reference frame that is moving in the positive x direction. So if a reference frame that has the same orientation of the axes, but the entire axes are now moving to the right in the positive x direction. That's the so-called primed frame. These are the transformations between the times and positions noticed that are measured in the original frame and the times and positions measured in the moving frame. And you'll notice that there's no effect on the y and z directions. Both observers measure those to be the same. But there is an effect on the time and the x. The x isn't too surprising, but the time is more surprising. And the effects have to do with that factor gamma and the speed of light. You'll notice gamma is in there and the speed of light is in there. But you'll also notice that if the speed of light is infinite, just imagine for a moment that the speed of light were infinite. If it were infinite, then gamma becomes 1 over the square root of 1 minus 0, regardless of your speed. Because if the speed of light is infinite, then it doesn't matter how fast you're going. 1 minus your speed squared divided by the speed of light squared is 1. 1 minus 0. So gamma is 1. If the speed of light is infinite, gamma is always 1. And if the speed of light is infinite, then that second term in the first equation, the Vx over c squared, is 0. If the speed of light is infinite, that term is not there. So if the speed of light is infinite, these equations, the first equation becomes t prime equals t. That means that both observers will measure time the same way. Well, that's what everybody always thought, right? Everybody always thought that every observer would measure the same time. And that's part of what's called the Galilean transformation. Everybody measures the same time. That corresponds to a world in which the speed of light is infinite, according to the Lorentz transformations. And if you look at the second equation, if the speed of light is infinite, that equation just becomes x prime equals x minus vt. And that is once again the Galilean transformation, because if somebody's moving to the right relative to you, then they're going to see whatever coordinate you see steadily reducing because of your speed. X minus vt just reflects the fact that anything at coordinate x is now becoming at a smaller and smaller coordinate in your reference frame. That just reflects constant velocity motion in the world which we all intuitively believe we inhabit. If I'm in a train moving towards San Francisco, then San Francisco gets closer to me, even though it doesn't get closer to Los Angeles. And that's all that second equation would be saying. But this is an example of what's called the Lorentz transformation. And so so we have to measure things differently now as a result of this 1905 equation. Okay, comments, questions? So what I want to say, I'm going to say a couple things here. I'm not going to support them as well as I probably should, but at least, especially this first thing. I want to talk. I had talked before about how in the corpuscular theory, the right way to think about aberration was simply to recognize that any observer had the perfect right to consider himself to be at rest, to consider that light to be just coming directly to him from the source where it was when it emitted that light. And that's indeed what you can do. In the corpuscular theory of light, every observer, as is kind of shown on those repeats from, I think, episode 2 of this series, every observer just, they may see things differently than other observers. They see light coming from different directions, but that's just because in their reference frame, that source was in a different position when it emitted the light. And that light is simply coming straight to them from where it was when it emitted the light. That's what particles do. Now, that didn't mean, you may remember, that we couldn't think of it in terms of this rainfall analogy, the idea that, you might say, so if I see light coming straight down, I can say that the reason you see it coming at an angle is because you are traveling through this rain and you have to tilt your umbrella forward to shield yourself from it. That's a perfectly valid way of looking at it from my frame, and I can calculate it that way, and I will get the right answer. But it's just important philosophically to understand that there's nothing privileged about your way of seeing it. So when you think that that other person is moving through the rain, that's just you thinking about it from your reference frame. They have every bit as much right to see it as you moving the opposite direction through the rain that they see, which they think is the actual primary rain. So it's, again, you get the right answer both ways, but the right way to think about it in the corpuscular theory is that the light comes straight to you. So as I say there, what about the moving through the rain? So then what I want to say is, what about moving through rain, which was the right way of thinking about it when you talked about the wave theory? Once you have the wave theory, then the light really is traveling in one direction in the right frame, and the only reason you might see it in another direction is because you're moving through that rain. And now that is the right way to think about it, even though, even in the wave theory, you can still also calculate it as if the light simply came straight to you from the source. So it's kind of an odd thing. There's a right way to look at it, but it doesn't matter which way you calculate it. It works either way. But what about this? So, as I said, in relativity, as in the corpuscular theory, the philosophically correct way to view aberration doesn't involve motion through the rain, because there's no such thing as absolute motion. There's only motion relative to another reference frame. But also in relativity, as in corpuscular theory, one will get the correct result by treating it that as if it is, as if you are moving through a rain. The difference, though, is that we now have to use a different velocity addition formula. In addition to the Lorentz transformation giving us kind of this bizarre new transformation that involves measuring times differently as well as distances, we now have a different velocity addition formula. In Galilean terms, we've talked about this before, the velocity of A with respect to C, that's what I'm writing there in the next equation, is just the velocity of A with respect to B plus the velocity of B with respect to C. So for instance, if I want to know how fast, if somebody is running toward the front of a train on a flat car and the train is moving down the track at 10 miles per hour or something, to find the velocity of the person on the train relative to me, I have to add the velocity of the person on the train relative to the train plus the velocity of the train relative to me. That's the import of those subscripts, the AC, AB, BC. And I mentioned last time that it's easy to remember if you just put the subscripts in that order. The two subscripts, the B subscripts cancel out when you add those two velocities, and you're just left with the original A and the final C. Nice way to kind of remember that. And it makes total sense, right? But in relativity, that equation gets modified, and I'm just telling you this. It's the same thing. It's the VAB plus VBC, but now you have to divide by 1 plus the product of those two velocities divided by the square of the speed of light. I'm just telling you this, right? It comes out of the Lorentz transformation. But that's now the velocity addition formula. And as one quick example, just consider what happens when the velocity of B relative to C is the speed of light. So I want to find out what the velocity of A with respect to C is. That's going to be the velocity of A with respect to B plus the speed of light divided by 1 plus the velocity of A with respect to B times the speed of light divided by the speed of light squared. And if you just just simplify that last term just becomes the velocity of A with respect to B divided by the speed of light. If you work out what that gives you that the velocity of A with respect to C is the speed of light. Oh, you know what? I realized I said consider. Sorry, I said consider what happens when VBC equals 1. That was my unfortunate prejudice. I often think of the speed of light as being 1. I meant to say consider what happens when VBC equals C. So sorry about that. There was a lot of confusion generated by that one, I'm afraid. Anyway, the point is that the velocity addition formula has the nice effect of confirming what you are assuming in the theory that generates it, which is that it doesn't matter how fast if you have somebody who sees something moving at the speed of light and you use the velocity addition formula, you'll find out that you see the speed of light too. You get the same velocity that they do. You can add velocities arbitrarily large and you'll never get a velocity greater than the speed of light using that formula. And the only reason I spent so much time on that is really for the final, the punchline here. So what about moving through the rain in the Fizeau experiment? Let's look at the Fizeau experiment. I'm going to use that velocity addition formula. This is the punchline of the entire series here. So pay attention. Get off your bike and put your thinking hat on. Consider the Fizeau experiment. If I let A be the light, B be the water, and C be the lab, then that velocity addition formula says that the velocity of the light with respect to the lab, how fast we would measure it traveling in the lab, is the velocity of the light relative to the water plus the velocity of the water with respect to the lab divided by 1 plus the product of those two things divided by the speed of light squared. So let's plug in what those are. The velocity of the light with respect to the water is c over n. That's just how fast light travels in water, is the speed of light in a vacuum, which is c, divided by the index of refraction of water. And the velocity of the water with respect to the lab is just the thing we were always calling v before. That's how fast the water is flowing. So I'm just going to put v in there. And then I have to divide by 1 plus the product of those two things divided by the speed of light squared. And I can simplify that by dividing one of the c's out in that very final term, and then it just becomes c over n plus v divided by 1 plus v over nc. Now, in the next step, I probably should have put a little thing on there. What I'm using is the fact, and you can check this out on your calculator, when you divide by 1 plus a small number, and notice v over nc is a small number. It's something like 10 to the minus 6th, 10 to the minus 7th, usually. So very small number. When you divide by 1 plus a small number, just take 1 divided by 1 plus 0.001, and what you'll get is 1 minus 0.001. Just if you've got a calculator handy, just check that out. But it's just a general rule. When you divide by 1 plus a small number, you get very close to 1 minus that small number. Now, there are terms that I'm ignoring there. There are higher order terms that I'm ignoring there. But to first order in v over c, and that's what we're always talking about here, to first order in v over c, that's what you get. So it's just c over n plus v times now 1 minus v over nc. And if I just multiply that out, I've got 2 terms in the first thing times 2 terms in the second thing. I'm just going to multiply all those out and get 4 terms, and I collected them together as shown. One of the terms is just c over n. That's big. That's the speed of light. That's almost the speed. That's hundreds of thousands of kilometers per second. And then there's 2 terms that are both on the order of v. One is v, and the other is v divided by, 1.5 squared or something. Those are just normal velocities. And then the final thing, if I arrange it properly, I get that it's v over n, which is a normal velocity, times a really tiny number. V over c is a really tiny number. So I've sorted out those four terms to show that the first one is really big, the second two are just kind of normal sized, and that third one is really, really tiny. So much that if I was looking for if I was looking for a deviation from the main result, that big number, I might be able to measure the normal number as an addition to it, but there's much less chance that I'll ever even notice that tiny number. So I'm just going to get rid of it and then write it as, and notice what I'm writing it as there, c over n plus v times 1 minus 1 over n squared. And this is the punchline. I'm sure you're all floored at this point. But just to be really clear on what we've done, we have used the relativistic addition of velocities to show that that is the reason Fizeau measured the speed of light to be what it was. It's not because of ether dragging. It's because of that's the fact that that's the way you add velocities in relativity. But notice that that equation is exactly the equation that we had on slide 4. C over n plus v times 1 minus 1 over n squared. And it is that 1 minus 1 over n squared that had always been a purely empirical thing. Fizeau said 100 years before this, Fizeau had said, that's what it has to be if I want to explain why Arago didn't see anything. And then why Airy didn't see anything, why all of those experiments failed. And it's what Fresnel confirmed the velocity to be. And Einstein would say, yeah, that's right, that was the velocity. But it wasn't because ether was being dragged. It's because when you add the velocity of the light with respect to the water to the velocity of the water with respect to the lab, that's what you get. That's what the addition of those velocities gives you. Okay. So as I say, relativity just reveals that Fresnel's partial drag, this massively successful thing that had never had a theoretical basis, it really isn't at all what Fresnel and everybody else thought it was. It's just the first order result of, and it is the first order. I should be clear on that. It's not even correct. If the velocities were larger, we'd have to take into account terms that I threw away in doing. There are two places at which I made approximations, and so I'd have to take those into account as well. But the point is that light moves at its full c over n relative to the water, and then the light is fully dragged by any medium that we see moving, and we just have to add those velocities relativistically to get the result. Okay, well, I don't know. I don't know that was as stunning a denouement as you might have been hoping for, but I think it's pretty cool ultimately to kind of have this sweeping explanation for things that had been successful for 100 years without actually understanding where they had come from. There were precursors. I mean, all of this stuff, the aberration itself is understood in relativity just the way it was from the beginning, with the addition of the fact that these waves are now traveling from sources that have to be repositioned using this non-intuitive Lorentz transformation rather than the Galilean transformation. Anyway, I just summarized this time just to say I have barely scratched the surface here. This has been, I really appreciate those of you who've stuck with me through this, because this has been probably in some sense an ego trip for me, just putting out there and trying to organize my own thoughts as I learn stuff that I never knew myself. And I think most physicists, frankly, don't spend the time to go back and kind of understand the painstaking work that was done in the 1800s especially, but also the 1700s to some extent, trying to come to terms with these strange observations that they had. So I do just leave you with kind of an obvious place if you're interested at all. The article on the luminiferous ether on Wikipedia does go over a lot of the same stuff that I've talked about here, with a lot more additions and, of course, references to other things. And I know I'm going to be mining it more myself. There's an endless. Oh boy. Okay, the guy's right next door now. Anyway, I'm gonna shut up for a moment. Maybe even turn my mic off and hope somebody else wants to say a few words. If anybody downstairs wants to come up, raise your hand. We saw Richard. We got Richard here too. Otherwise, I'm going to shut up for a moment and see if we can. Oh, it looks like maybe he's already done. But I'm done. Thank you for your patience.
Thank you, John. That was wonderful, actually. Fresnel had theorized for special relativity producing that effect without him knowing what he was theorizing for. Like, he just an empirical number guess, and it turned out to be the transformation that relativity produces.
Yeah, that's right. And it's probably the best example of that. But the really interesting thing is I think for me, one of the interesting things, going back and seeing all of the things these people saw, trying to see them with their eyes at the same time that I can kind of smugly sit back here and say, oh, that's so cool. That's relativity. And they didn't even recognize it. Right. And I think Fresnel's is the best example of that because of that weird 1 minus 1 over n squared. It's there's an actual formula there, which it's like what it's very much like is Kepler's laws. Kepler looked at the orbit of Mars and maybe some other things. It's an astonishing thing that he did. He looked very carefully at the orbit of Mars from a moving platform from the Earth, right? And he worked out this idea that, first of all, its orbit was an ellipse, and that maybe that was the case for all the planets, that the periods of those orbits squared were proportional to the radius of the orbits cubed, in particular, the semi-major axis of that elliptical orbit cubed. And he got that somehow. And the idea that the line to the sun sweeps out equal areas in equal times. He just found all three of those laws empirically by just looking at something that would fit the observations. That's all he was doing. And it turns out that all three of those three laws are completely sufficient to describe any orbit. And all three of them come out precisely as he stated them from Newton's laws. And it's just, to me, that's one of the most astonishing things in all of science. What Kepler did was extraordinary because he was exactly right. There wasn't an element of what he did that was wrong. He got the equal area thing is exactly conservation of angular momentum. The elliptical orbit thing is what you get from solving the second order differential equation that is Newton's law of gravity combined with Newton's second law of motion. What was the third? Oh, and the periods. Yeah, same thing that comes out from the same thing, but in specific detail. It wasn't an approx. He thought he was just he was just trying to find something that would work. He had no understanding of why it worked. He could have been wrong by a little bit here or there, but it was exactly right.
And he didn't have spreadsheets. Like, I could imagine doing some data fitting today with a huge amount of data, and then you have the spreadsheet thingy, and then you have a guess, and you produce the guess minus some other guess, and you see whether the actual thing fits the guess or not. Oh, look, I have the right guess. But doing it with pen and paper without
Unbelievable.
electricity, that's just something.
It is. I mean, this is a guy who had to do this, day and night for decades, right? To kind of do the calculations, as you
Every
say,
time
pen and
you forget a
paper.
minus,
Oh
every
my
time you forget
God.
a decimal point, you got to restart the entire thing.
Yeah.
It's just and you don't even have ball pens. You're writing with these quivers, whatever you want to call them, and you're smudging the paper with ink, which is not really paper. It's just something very thick and smelly. It's just unbelievable.
It is. It's
That man,
mind
as you say,
boggling.
yeah, yeah.
It is mind boggling. I honestly don't think anybody, no living human being could possibly do, that could put that kind of mental effort and the kind of, yeah, I mean, just without the tools, right? Today we have the tools. Even with the tools, what he did is difficult. Without them, it just seems impossible. To me, it's mind boggling. So. Yeah, and the Fresnel thing is a little hint of that. The difference is that in the case of Fresnel, he didn't get it exactly right. He got it right to first order in V over C, and it's just because nobody had been able to had an experiment sensitive enough. If they had, they would have seen that there were deviations from Fresnel's that are in line with what the relativistic prediction is to higher orders in V over C. Anyway, yeah, maybe enough said. Any other comments? Maybe I have a gig tonight, so I have to do some wood shedding before that. And I've got these tree guys here, so I probably need to talk to them too. Shall we say goodbye until next week? I don't know what may happen next week. It's possible I'll even take a week off after all this, but check in at 9:30 next week, and we'll see if we come up with something.
Cool, cool. We'll be there. Never gonna miss it for the world.
All right, thanks, Shamash, and thanks for all you do. You put yeah, I should certainly finish with that. Once again, Shamash puts in Keplerian kinds of efforts, putting these things online on the Scientific Discourse channel on YouTube. So they're also available there, along with his own Philosophy of Wednesdays. And I think Sam Tomasi, you putting Sam's up as well? Sam Tomasi's
Yeah, I
chemistry.
started doing so. I'm gonna start doing a lot more effort starting Monday because I'm off the full time for now. So I'm gonna be left at home to do whatever. And so more episodes will be posted over
Okay.
the week. But yeah, at least like I think 5 or 6 of Sam's lectures are already online.
Okay, good. You want to tell us what you're thinking about for next week?
Yeah, sure. If you've been attending the Philosophy Wednesdays, we've been doing this review over the theories of science. I kind of alluded to in the middle there. John was asking me. We were focusing essentially the last 2 weeks on probabilistic frames of knowledge or doing science, let's call them. And of course, the most famous of them is Bayes' theorem and Bayesian epistemology. And last time I started kind of criticizing it as a school of thought or as a philosophy of science, and we're going to finish that. So I couldn't finish the presentation. We went on for 2.5 hours. Some details were. Can I say I really I'm really I don't want to say that. I really envy you, John. Like you have these presentations and you load them with math, and nobody asks anything. And I had 2 lines of calculations last time, and it was like an hour before we cleared those simple, straightforward math. But anyway, so because of that, we need to extend it for one more room. So next Wednesday we will be talking about Bayesian frame. I'm expecting to finish early, and then we can have a bigger discussion than usual. That's the plan.
Can we talk about the Monty Hall problem some more next week too?
Yeah, sure, of course, as much as you want,
I
as much
love
as
it.
you want, Monty Hall.
I just love
The
the
Monty
Monty
Hall
Hall
is
problem.
the Monty Hall is amazing. I had so much fun again. Playing with students and asking them to do it. It's so fun.
All right. Well, thanks everybody. Sorry.
Yeah.
Yeah. So I think I will play us out maybe with my kind of all-time usual Gravity tune, because we're right on the verge here. We're only 10 years away from Gravity now at 1905, where we ended this series. Thanks for coming. We'll find other things to talk about in the future, and we will see you next week.
Remember that.
Oops, wrong one. Ah, why not? We'll play
Yeah,
out with
let's
that.
do it.